Hello everyone, welcome to Sai Tutorials Jamkandi. In our tutorial, 10th class Kannada medium, English medium, math, science, English classes are available in the regular classes as well as in the online classes. So dear students, today I am going to discuss about the next concept related to your first chapter, that is electric field and charges. In yesterday's class, in the previous sessions, we have discussed something like that. Principle of superposition of electric forces, electric dipole, and some of the applications related to the field at a point on the axial line of electric dipole and a field at a point on the equatorial line of dipole, field at any point due to a dipole. So in today's class, let us discuss torque on dipole in an electric field. Torque on dipole in an electric field. See, what is torque on a dipole in an electric field? Which is the main important concept related to your syllabus, that is torque on dipole in an electric field. See, when an electric dipole of moment p bar is held at an angle theta with the direction of a uniform electric field E bar, torque acts on the dipole which is given by tau. The representation of the torque is tau bar is equal to P bar into E bar, where P bar is the dipole and E bar is the electric field. So it is equal to PE in the magnitude, it can be represented as PE sine theta. The torque tries to align the dipole in the direction of the field. So in an easy way, I'm going to tell you that suppose some electric field is passed or some electric field is present in something like, okay, so let us consider some field lines. The electric field is present over something. That is, consider an electric dipole consisting of the two charges. Okay, let us consider an electric dipole consisting of two charges. This is plus Q and this is minus Q, which are separated by a distance 2D. Okay, which is separated by a distance 2D, which are held perpendicular at an angle theta. Perpendicular at an angle theta. Direction of electric field E bar, the force acting on the charge plus Q is the force. Okay, the force acting on the plus Q charge is Q into electric field E bar. Okay, in the same way, the force acting on minus charge towards this side, that is minus Q into E bar. Now, these forces are having equal magnitude. These two forces are having equal magnitude but in the opposite direction, constitute a torque. Okay, these two charges, these two forces are having equal magnitude but having the opposite direction, constitute a torque. Constitute a torque. This is the concept, that is torque. See, consider the two charges plus Q and minus Q are separated by a certain distance 2D and which is placed in a uniform electric field. Okay, this is which is placed in a uniform electric field making an angle theta. Direction electric field E bar, the force acting on plus Q is Q E bar and the force acting on minus q is minus q e bar. These forces are having equal magnitude but opposite direction constitute a torque. So, when an electric dipole of moment p bar is held at an angle theta with a direction of a uniform electric field, a torque acts on that dipole, which is given by torque tau is equal to p bar cross e bar is equal to p e sine theta in magnitude. See, another important point to note here is the torque tries to align the dipole in the direction of the field. See, the torque which is held along the direction of that electric field. So whatever the electric field is passing, so in that direction only the torque is also going to act. So suppose this is at the point, suppose let us consider it as point A and let us consider it as point B. And suppose the plus q charge is placed at that point B and minus q charge is placed at that point minus q, then the electric field is in this direction, right? The electric field is in this direction. Then the torque is also tries to align in the same electric field direction. So this is all about the torque acting on dipole in an electric field. Have you got this? I hope this concept is clear to you. The next and for most important concept that is related to your syllabus is electric field due to a continuous distribution of charges. That is electric field due to a continuous distribution of charge. In what way it is going to happen? So if a charge Q is distributed uniform over a body. So let us consider a body which is having number of charges, whether it may be positive charges or negative charges. Okay, like Q. If a charge Q is distributed uniformly over a body, then the electric field at a point P distance r from an element with a charge dq in the body is given by dE is equal to 1 divided by 4 pi epsilon naught into dq divided by r square. Why this is written like this is because in a large body or in a large length of the body, any length of the any substances or in a surface area of the body or in a volume, if we consider the small volume or a small area or a small length, then the charge is going to be written as dq. Okay. Similarly, then the electric field of that small body or a small length or a small area or a small volume will become dE. So that's why this is to be keep in mind that if a charge of a small body we have considered, then the charge of that small body will be written as dq and the electric field of that small electric field is dE. So let us discuss one by one here. So dear students, first of all, let us take an example with linear or one-dimensional distribution of charge. For linear distribution of charge, okay, let us consider a small charge in a linear distribution. For linear distribution, let us consider when a charge is uniformly distributed over the line, let us consider the line. Consider a straight line wire because the linear distribution of charge to be said. So consider a straight line wire AB. This is A and this is A and this is B. Am I right? So it is having the length DL. This is having the length L. Okay. On which a charge Q is distributed uniformly. Suppose let us consider charge Q like this. Okay. Charge Q is distributed over this length. Now, Let lambda is equal to the linear charge density. Okay, let us consider lambda is called the linear charge density. Let us consider the lambda is equal to linear charge density. That is, what is the formula for linear charge density? I mean, charge divided by length. That is Q divided by L. It is the linear charge density. Now consider a small element of length. I have said you that in any linear or a surface area or in any volume, we need to consider a small distribution of charges for a small length. Let us consider small length, that is dl. Okay, small length dl. This is a small length. Now a small element of length dl on the wire, charge on that element of the length will become dl. Am I right? dq. Now dq will be written as the charge linear charge density into dl. Linear charge density into dl. Then the electrostatic force on charge q placed at a point p at a distance r from the small element is given by. Now let us consider a small point p at a point p which is having the charge minus q naught. Okay, minus q naught. Then the electrostatic force will become 1 by electrostatic force will become df bar is equal to 1 divided by 4 pi epsilon naught into small charge dq cross at a point P which is having the charge q naught whose whose distance from that point is r. So divided by r square into, in the vector form we need to write r cap here. So this is all about the linear distribution of charge. See, if consider the 2 point charges A and B separated by a distance, I mean which is having the wire. Okay, let us consider the length of the wire AB which is having the length L. A charge Q is distributed uniformly over that length L wire. So let us consider the small length dl and whose charge is placed at a point P, that is Q naught, now which is whose distance is R. Okay, then the linear charge density dq of the linear charge density of that small length will become dq is equal to lambda into dl. Then the force, electrostatic force acting on that linear distribution of charges will become 1 by 4 pi epsilon naught into dq cross q naught divided by r square into r cap. This is the for linear distribution of charge. I hope this concept is clear to you. Now, the next concept, I mean, the next important thing in the same way we need to consider for surface distribution of charges. Just a second. Okay, the second thing, that is the surface distribution of charge dq is equal to sigma into ds where sigma is called the surface charge density. Then in the same way, okay, in the same way, when a charge is continuously distributed over uniformly over a surface, we call it a surface charge distribution. Suppose let us consider any surface area. Okay, let us consider any surface area which is having the charge distribution uniformly let us consider a plane sheet. Okay, let us consider a plane sheet of a surface area whose surface area is S. Okay, whose surface area is S, on which a charge Q is uniformly distributed. I have said you the charge Q is uniformly distributed. So let us consider sigma. Okay, let us consider sigma, that is surface charge density, which is equal to the charge by area, charge by area of that surface. Now consider a small element in the in the sheet of a paper. Yes, let us consider a small surface. Okay, this is a small surface whose charge is placed at a point P, placed at a point P, which is having the charge Q naught. Then the charge for that particular small area will become dq is equal to sigma into the small surface, that is ds, where sigma is called the surface charge density. Then how do you calculate the electrostatic force on that particular small surface area? So it will become df bar. Okay, df bar is equal to 1 by 4 pi epsilon naught dq into q naught divided by r square into r cap, or it can be written as 1 divided by 4 pi epsilon naught sigma into dq. What is dq? Sigma into ds. Sigma into ds into q naught divided by r square into r cap. So this is the force acting on that small surface area. So this is an electric field due to a continuous charge distribution of distribution of charges in case of surface distribution of charge. Okay, this is a surface charge distribution of charge. In the same way, how do you find the volume distribution of charges? So let us discuss volume distribution of charges. In the same way, when a charge is distributed continuously over a volume, then we will call it as volume distribution of charges. So let us consider any volume here. Any volume, it may be in any shape. So in which a charge are uniformly distributed. Just a second. Where a charge is uniformly distributed. In a value, the charges are uniformly distributed. Suppose in that a large volume, we consider the small length, small volume. In that large volume, we consider the small volume. Then the charge dq, okay, the charge dq of that volume will becomes rho into dv. Am I right or not? Rho into dv. Why I have written this? Because rho is called the volume charge density. Volume charge density, the electric charge of that small volume will become rho into dv. So then the force, electrostatic force acting on the, say, whose charge is placed at a point, whose charge is placed at a point P at Q naught. Similarly, Q naught, then the electrostatic force at that small volume will become dF bar is equal to 1 divided by 4 pi epsilon naught into dq cross a small charge at a point pq naught divided by, which is separated by a distance r, it is r square into r cube in the vector form. So if you substitute the dq value, this is dq value, you will get the volume distribution of charge at a point dq. So df bar will be 1 divided by 4 pi epsilon naught into rho into dv into q naught divided by r square into r cap. This is all about the electric field due to a continuous distribution of charges. I hope this concept is clear to you guys. The next important concept, that is electric polarization, dielectric polarization. That is dielectric polarization. Okay, see, we have two phenomena, that is one is dielectric and what is polarization. Say dielectrics, what do you mean by dielectrics? In the previous sessions I have discussed you about dielectrics. So dielectrics are non-conducting substances, which will not conduct any electricity. Such a substances are called as non-conducting substances or a dielectric substances. In contrast to conductors, they have no charge carriers or a negligible number of charge carriers are there. Then such a substances are called as dielectrics. Then what do you mean by polarization? See, polarization is nothing but the dipole moment per unit volume is called as polarization. Okay. See, dielectrics are non-conducting substances. In contrast to conductors, they have no net charges or they have no charge carriers. But we are coming to the polarization. The net force or the dipole moment per unit volume is called as polarization, and it is denoted by the letter P. P bar. That is dipole moment per unit volume. And for linear isotopic dielectrics, that is P bar is equal to xi or they have written here alpha, or we can also write it as xi e. Susceptibility, we will say this is the susceptibility constant, electric susceptibility. So into electric field. Dielectric polarization is called as when a non-polar dielectric slab is held in electric field. See, let us discuss the four important phenomenon here. One is dielectric, I have said you. Second one is polarization, I have said you. And the third thing is polar molecules. What are polar molecules and non-polar molecules? Okay, what are polar molecules and non-polar molecules? Polar molecules. A polar molecule is one in which the centers of positive and negative charges are separated. So such a molecules are called as polar molecules even when there is no external field. See, a polar molecule has a permanent dipole moment. I have said you a polar molecule is one in which a centers of positive and negative charges are separated. Suppose this is positive charge and this is negative charge whose centers are separated even in the absence of electric field or in the absence of external field. So such a molecules are called as polar molecules. A polar molecule has a permanent dipole moment. Okay, a polar molecule has a permanent dipole moment. For example, water H2O molecule. For example, H2O and HCl, etc. So what do you mean by polar molecules then? A polar molecule is one in which the centers of positive and negative charges are separated even when there is no external field. So such a molecules are called as polar molecules, and the it has a permanent dipole moment. Such a molecules are called as polar molecules. Example, H2 and HCl, water and hydrochloric acid. So this is the polar molecules. Then coming to the non-polar molecules. Opposite to that polar molecules. See, a non-polar molecule is one in which the centers of positive and negative charges are coincide. Coincide means they will coincide. Such a molecules are called as non-polar molecules. See, a non-polar molecule has no permanent dipole moment, whereas polar molecules has a permanent dipole moment, but non-polar molecule has no permanent dipole moment. Examples are oxygen and hydrogen. Oxygen and hydrogen. These are the examples for non-polar molecules. So we have discussed the one is dielectrics, what is dielectric substances, and polarization. What do you mean by polarization? Polar molecules and non-polar molecules. Then coming to the concept, dielectric polarization. Dielectric polarization when a nonpolar dielectric slab, okay, when a nonpolar dielectric slab is held in an electric field E naught, in vacuum, the dielectric slab acquires a net dipole moment. The induced dipole moment can be written as P bar is equal to alpha into E naught, where alpha is a constant of proportionality called atomic or molecular polarizability. See, I have said you a polar and non-polar molecules. So in the same way, they have considered when a non-polar dielectric slab is held in an electric field E naught in a vacuum, the dielectric slab acquires a net dipole moment. Okay, there dielectric slab acquires the net dipole moment. The induced dipole moment can be written as P bar is equal to alpha into E naught, where alpha is a constant of proportionality called atomic or molecular polarizability. Therefore, the effective field in a polarized dielectric slab decreases. So after acquiring the net dipole moment, the electric field in a polarized dielectric slab is going to decrease, which can be denoted by this. That is, E is equal to E naught minus EP. That is the electric field E naught and EP, where EP is the induced electric field. It is an induced electric field, and also EP can be written as sigma P divided by epsilon naught, where sigma P is the surface density of polarization charge. Please note down this sigma P. Okay, sigma P, that is surface density of polarization charge. So now the ratio of E naught divided by the electric field E is equal to constant K, is called as a dielectric constant. See, when a nonpolar dielectric slab is held in an electric field E naught in a vacuum, the dielectric slab acquires a net dipole moment. The induced dipole moment will be P bar is equal to alpha into E naught, where alpha is called a constant of proportionality called the atomic or molecular polarizability. Therefore, the effective field in a polarized dielectric slab is going to decrease after acquiring a net dipole moment. It will become electric field is equal to E naught minus EP, where EP is the induced electric field, and then EP is given by sigma p divided by epsilon naught, where sigma p is the surface density of polarization charge. So what do you mean by say epsilon naught? Then it is a permittivity of free space, that is in a vacuum. The ratio of E naught divided by the electric field E bar E is equal to K, where K is called as a dielectric constant. This is all about the dielectric polarization. So for dielectric polarization, we need to know the concept. First is what are dielectric substances, what is polarization, what are polar molecules, and what are non-polar molecules. So by combining these four properties, we can derive the expression, or we can know the concept, that is dielectric polarization. So I hope this concept is clear to you guys. So by this, let us going to stop here. I'm going to wind up the session here. So in tomorrow's class, I'm going to discuss about electric field lines. It's a very important concept. It's a very important concept. So in the next session, let us discuss electric field lines. So I hope the electric field due to a continuous distribution of charge and torque on dipole in an electric field, and also dielectric polarization is clear to you guys. I hope this session is very helpful to you people. So thank you. Please don't forget to subscribe our channel.